This lesson is on topic 1.2, measurement and uncertainties. What we will be focusing on here are the various understandings. We need to be able to differentiate between random and systematic errors, and we also have to deal with the fact that the data that we have will have uncertainties. There's a difference between an absolute uncertainty that we'll find out about, as well as fractional and percentage uncertainties. And those uncertainties will carry through into our conclusions and our results. Because if your data is uncertain, there is no way that your results can be certain. Okay, we'll also look at error bars and the uncertainty of gradient and intercepts. We use the term gradient here to mean this exact same thing as slope. So remember, when we linearize our data, we now have a line with a slope and a y-intercept and an x-intercept, but we're usually only concerned with the y-intercept. So those uncertainties will carry through to what is my slope exactly. It's not, there is no exact, it's within a range. And same thing with our intercepts. Okay, we'll apply this knowledge in determining how can I reduce the possibility of random and systematic errors in my labs. What can I do to my methods? Okay, and we'll also be looking at that and propagating how do I carry that uncertainty in my data all the way through to my conclusions and my results. Okay, first off, all measurements are made with instruments and read by a human being. The answer is never going to be exact, but it's going to be subject to a precision. For electronic instruments, the precision is usually printed on the instrument. So otherwise we use the smallest digital increment, plus or minus 0.01 seconds. In a digital stopwatch, it reads down to the hundredths of a second. So 0.01 seconds, okay, pretty good. Understand though that is the precision associated with the instrument. Your ability as a human being to hit the stopwatch at the exact correct time is not anywhere close to 0.01 seconds. It's actually closer to 0.1 seconds or 0.2 seconds. Okay. For manual instruments, the precision is going to be a little fuzzier. It's your ability to estimate it. Usually it's about half the smallest increment, but you could estimate smaller or in some cases slightly larger. So for example, okay, in the first measurement, it's somewhere between 9 and 10. Okay, it looks almost half. If you look a little closer, it's a little bit larger than half. So maybe 9.5, 9.6. In the second case, okay, so here 9.5, 9.6. In this case, it looks to be pretty good to 8.5. If you wanted to shade it a little bit less, 8.45 maybe. Okay, and in this case, it looks somewhere between 11.8 and 12.0. So let's call it 11.9. Okay, so these are examples. They don't have to be the same for everybody. And for the first one, you could have estimated it at 9.5 instead of 9.6. Or you could have said that the uncertainty, I'm pretty good with this. Okay, I'm pretty sure it could be 9.6 plus or minus 0.1. The real value then is somewhere between 9.5 and 9.7. But my eyes aren't that good, so I'm going to call it somewhere between 9.4 and 9.8. I'm pretty sure it's in that range. Same with the 8.5. It looked maybe a little bit less. If you wanted to have called it 8.45 plus or minus 0.05 centimeters, okay. But for me, 8.5 plus or minus 0.1 sounds good. Same with in number C, letter C. It's 11.9 plus or minus 90 plus or minus 0.05. Note that your uncertainty, hundredths, and your measurement must always agree in the same decimal place. Okay, they all agree. Tenths place, tenths place. Tenths place, tenths place. Hundredths place for, let's see. Okay, so uncertainty represents the fact that the actual value is somewhere in that given range. If I have a lot of data, I can use statistical methods like mean and standard deviation. Okay, if I have that and choose standard deviation plus or minus 2 times that standard deviation, what that means is there's a 95% chance that a measurement you make will be inside that range. If you want a little bit more likelihood, you can go out to 3 times standard deviation, and that'll give you about a 99% chance that the actual measurement is in that range. So plus or minus 3 times if you really wanted to be sure. Okay, the difference between accuracy and precision. When I make a measurement, okay, multiple times, then accuracy tells me how close is that measurement, or how close is that average of those measurements to the actual value. Okay, so for example, if the center of the target is my actual, okay, then A and C, when I average them out, the center of the target, okay, that's pretty good. Those two targets are considered to be accurate. So A and C are accurate. But accuracy is a relative term. You can only say something is more accurate or less accurate. Okay, something is more precise or less precise. So in the targets shown below, B and D, A and B are clustered very closely together. They're very precise. Your ability to duplicate your measurement or duplicate your target is pretty good. D is very poor precision, okay? It's spread way out. I've got shots in the outer ring on the left side, shots on the outer ring on the right side. It's pretty bad, okay? It's important to note, though, that accuracy and precision don't have to correlate. I can have both of them being high, relatively high, as in A. They can both be low, as in D, or different, as in B and C. Okay, so be able to distinguish between accuracy and precision, because random error starts to affect that. Okay, it's exactly as the name says, it's random. Sometimes it'll be high, sometimes it'll be low. Okay, it's almost impossible to eliminate it. You can reduce it. One way of reducing it is by taking lots and lots of measurements. Okay, that's what we did with the sphere of clay. Okay, if I made a bad measurement, I could have taken one. If I only took one measurement, I took the long side. Okay, by taking multiple measurements, I could take the long side one time and then the short side another time. The thing is, it's not a clear, perfect sphere. Okay, so the random measurements we choose take into account that it's not a perfect sphere, and so it allows us to average long measurements and short measurements instead of just one. Systematic error is different, okay? It's not random, but due to the design of your experiments. Sometimes we can fix these errors. A calibration error is an example of a systematic error. So if we check our equipment beforehand, we eliminate those. But it's important to note that the errors are almost always high or always low. You're always going to be measuring something that's too high than the actual value, or something that's always too low to the actual value. Okay, so for example, if I'm calculating density, the scale is miscalibrated, it's 5 grams too high every single time, okay? Or a pressure gauge that I'm using and it's calibrated for 20 degrees Celsius, but my room is actually at 25 degrees Celsius. Different aspects of your methods and procedures can and will impact your systematic error. Okay, the evaporation, okay, I measure the volume, some of a liquid, and some of it evaporates between the time I measure the volume and bring it over to the scale and measure its mass. Okay, not all systematic errors can be fixed, even in the most high-tech of labs. With the tools that we have in our high school lab, yeah, we're going to have a lot of systematic errors. That's okay. It's a high school lab after all. But what's important to do is to recognize the presence of those things and the impact of that error. Is my measured value going to always be high, or is it always going to be low? Is the impact a lot, like I'm way off, or is it a little? Okay, what can I do to make the impact as little as possible? And because of that error, is my result always going to be high or always going to be low? That's what we need to focus on when it comes to the systematic errors. Human error is something that comes up frequently, okay? Human errors are mistakes that happen because we are human. I spilled the beaker between measuring the volume and the mass. I used the inches side of the meter stick. Okay, I put the apparatus on setting 2 instead of setting 3, or I used the calculator wrong. Okay, those errors do not show up in our lab reports. Never. Okay, because if you make those types of errors, you can also fix those types of errors. They're always fixable and they must be fixed. If you make a trial with a human error because you spilled the beaker, those trials don't count. Repeat the experiment or repeat that trial. Okay, human error is never a valid reason that an experiment fails. You must fix them. Okay, so human variability, however, okay, those are part of the methods and procedures, and there's nothing we can do about that. Okay, so human variability, like the reaction time, hitting a stopwatch, or reading the volume of a liquid, those are factored in as random errors. Okay, not the human variability, but human errors because of mistakes we did in our methods and procedures. Okay, those we must fix. So that brings us to uncertainty. Okay, the uncertainty of a measurement. Okay, I'm measuring something. Okay, this is different from the uncertainty of whatever tool I'm using to make the measurement. In our Play-Doh lab, okay, the uncertainty, the measurement I was trying to make was the diameter of a sphere of clay. Okay, that had uncertainty because the sphere was not a perfect sphere. I had long sides and short sides, and it, in some cases, it may have been more elliptical. Okay, but that's fine. Okay, we were approximating it as a sphere, but I want to eliminate the possibility with one measurement I could have chosen just the long side or just the short side. By you taking multiple measurements, I'm taking an average and hopefully eliminating some of that possibility. Okay, but as I'm using the tool, you must pay attention to how that tool is used. Okay, so for example, if I use a stopwatch, human reaction time must be estimated. In general, human reaction time somewhere about 0.1 to 0.2 seconds. Okay, we're not the fastest things. If you're able to use some sort of electronic timer, microphones to record sounds, different things like that, those are better at being able to estimate the time than using a stopwatch. Okay, so pay attention to the tool's uncertainty as well as the measurement's uncertainty. It is impossible for your measurement uncertainty to be more precise than your tool's uncertainty. Okay, if all your measurements are 9.0 plus or minus 0.1, 9.0 plus or minus 0.1, yeah, it's pretty repeatable, but you never knew what the first one was in the first place. So the measurement uncertainty is always going to be limited by your tool uncertainty. And those uncertainties must propagate from your data all the way through to your results. Okay, and every time you do a math step, it's going to be important to propagate that uncertainty. Okay, and there are basically a few rules associated with propagating uncertainty. First, we have to deal with a couple of definitions. The first definition is absolute uncertainty. This is the standard uncertainty that we're used to. Okay, both your measurement and your uncertainty have the same units. Okay, so it's 5.25 meters plus or minus 0.01 meters. Okay, don't say 5.25 millimeters plus or minus 1 millimeter. Yes, 1 centimeter. It's the same thing, but always keep them at the same unit. Okay, they should also correspond to the same last digit. When you present data in any of my lab reports, okay, make sure you have the uncertainty and make sure that they correspond in the same units place, okay? In this case, they both correspond to the same hundredths place. Okay, so that's absolute uncertainty. Relative uncertainty is expressed as a percentage. It gives you a better sense sometimes of how accurate a measurement or how precise a measurement actually is. Okay, and basically it's expresses your uncertainty, your absolute uncertainty, as a percentage of your measurement. So example, here I have 5.7 plus or minus 0.1 newtons. Okay, if I take 0.1, what percentage of 0.1 is 5.7? Okay, it turns out after I do the calculation, it's about 1.8%. Don't bother expressing your relative uncertainty beyond the 10th place. Okay, the equipment that we're using is just not that precise. Leave it at about the 10th place or 2 significant digits. Okay, but what's important to realize is that 0.1 newtons out of 5.7, that's not too bad. But if it was 1.0 plus or minus 0.1 newtons, now I'm all of a sudden up to 10% uncertainty. If it was 0.1 newtons plus or minus 0.1 newtons, now I'm up to 100% uncertain. That's not a real good measurement. And there will be times that that's what's going to happen with our measurements. Okay, so to calculate absolute uncertainty from relative, we need to be able to go back and forth. We basically take the percentage and multiply it out to get our absolute. So 3.67 seconds plus or minus 6%. Okay, well 6% is 0.06 or 6 over 100. Multiply that out and I end up with about 0.2202. I'm not going to go that far out because I have to make sure my decimal points match. Okay, so same decimal place, in this case the hundredths place, so I'm going to just round that 0.2202 to plus or minus 0.22 seconds. Okay, so when I add two numbers with absolute, add any two measurements, okay, or subtract. Okay, remember subtraction and addition are the same function. Okay, then I have to work with the absolute uncertainties. Okay, 1 meter. Okay, it's really 999 millimeters or 1001 millimeters. Okay, plus another meter plus or minus 0.001 meters. That you add the measurement. In this case, it becomes 2, and you add the absolute uncertainties. It becomes 0.002. Okay, when I'm doing a multiplication, I have to work with the relative uncertainties. Okay, so in this case, 10.35 plus or minus 2% times 8.42 plus or minus 0.1%, okay, becomes 87.147, okay, meters plus or minus 2.1%. Okay, and I have to make sure that I round it I have to pay attention to significant digits. Okay, so really 87.147, this is wrong. It should really be 87.2. Okay, it should have 3 significant digits, as does this. And notice my relative uncertainty got added. 2 plus 0.1 becomes 2.1%. When I have numbers taken to an exponent, squared to the 1/2, cubed, okay, a number taken to the exponent, okay, then we basically just multiply the relative uncertainty by that exponent. So in this case, I have 7.125 seconds plus or minus 5% squared. Okay, so I want to take this 5 and multiply it by the 2. In that case, 7.125 becomes this. Okay, and then my absolute uncertainty gets multiplied by 2. 2 times 5 is 10. So that's where that comes from. And I have to round that to my original precision. Okay, or pay attention to significant digits. So my original precision had down to the 1,000th seconds. So I want to keep it at 1,000 seconds. Or using sig figs, it becomes 50.77 plus or minus 10%. Okay, thank you.